Testing 1, 2, 3. Okay. Hi. I'm back. There's something wrong with my chat widget thing. I don't know if I can fix it. I'm gonna test chatting, just like test 1, 2, 3. Okay, at least the version that's on the screen works fine. But for some reason, I'll have to go to either Twitch or YouTube to see chat. I can't see. I mean, I guess I can make the screen bigger, the OBS screen. Yeah, I don't think it's readable. It's possibly readable. We'll try. Okay. I still have a bad mic. Hopefully you can hear me. Testing. Yep. And I like my glasses. Yep, that's a motorcycle, and I bet it's really loud. Yeah. Today, I sort of forgot that I was planning to stream, so it's like 1 hour later than my usual time. So, and when I woke up, I was not feeling well, but I still wanted to stream because I'm excited about stuff. So I'm like, I have a blanket on, I'm cozy, and I'm like, coffee is here also, and dates, because I like coffee with dates. And it was raining this morning, which is surprising. Yeah. Okay. Like, it's May, so raining is a bit surprising. Okay. So we did at the usual intro. This is Introduction to Machine Learning for Coders by Jeremy Howard. It's taught by Jeremy Howard, and it's from fast.ai. Cool. Oh wow, OpenAI. Cool stuff. Oh shoot, what did I do? Anyway. Yay, that's cool. And I will say I have not been the most how do I say it? Like, I haven't taken it as a real student. I haven't been the most active participant, that's the word. I've been taking it a bit passively and sporadically, like in the span of 6 months. So if I don't get good, it's my fault, not the course's fault, because Jeremy Howard is a great person, and he has recent tutorials on his YouTube channel that are probably more updated. So yeah, this is 2018, and they have a lot more lessons. I mean, not this, like courses. There we go. That's the word I was looking for. Okay, so this is the last lesson. I don't think I'm gonna finish it today, but we'll try. And half of it is just solving something, I think, from a Kaggle competition. The other half is ethics. So let's start.
I thought what we might do.
I always very sneakily make this 1.25 and see if people notice, because I like listening to things sped up. Okay. I don't think I have this lesson opened up actually. No, this is from the last lesson. Let's see if it's needed, or if I can be just a passive student again.
Today is to finish off where we were in this Rossmann notebook, looking at time series forecasting and structured data analysis. And then we might do a little mini review of like everything we've learned.
I love a mini review. Wow, okay.
Because believe it or not, this is the end. Like there's nothing more to know about machine learning other than
This is the end. Hold your breath and count to 10. Okay.
and everything that you're going to learn next semester and for the rest of your life. But anyway, I got nothing else to teach. Yeah, so we'll do a little review and then we'll cover like the most important part of the course, which is like thinking about like how are ways to think about how to use this kind of technology appropriately and you know, effectively in a way that's hopefully a positive impact on society. So last time we got to the point where we talked a bit about this idea that when we were looking at like building this competition months open derived variable, that we actually truncated it down to be no more than 24 months, and we talked about the reason why being that we actually wanted to use it as a categorical variable, because categorical variables, thanks to embeddings, have more flexibility in how the neural net can use them. And so that was kind of where we left off. So let's like keep working through this, because what's happening in this notebook is stuff which is probably going to apply to most time series data sets that you work with. Right? And as we talked about, like although we use df.apply here, this is something where it's running a piece of Python code over every row, and that's horrifically slow, right? So we only do that if we can't find a vectorized pandas or numpy function that can do it to the whole column at once. But in this case, I couldn't find a way to convert a year and a week number into a date without using arbitrary Python. Also worth remembering this idea of a lambda function. Anytime you're trying to apply a function to every row of something or every element of a tensor or something like that, if there isn't a vectorized version already, you're going to have to call something like dataframe.apply, which will run a function you pass to every element. So this is something like, you know, kind of, this is basically a map in functional programming. Since very often the function that you want to pass to it is something you're just going to use once and then throw it away, it's really common to use this
Inline
lambda approach. So this lambda is creating a function just for the purpose of telling df.apply what to use, right? So we could also have written this in a different way, which would have been to say define create chromo 2 since on some value, return and then we could put that in here. Okay, so that and that are the same thing. Okay, so one approach is to define the function and then pass it by name, or the other is to define the function in place using lambda. All right, and so if you're not comfortable creating and using lambdas, you know, good thing to practice, and playing around with df.apply is a good way to practice it. Okay, so let's talk about this durations section, which may at first seem a little specific, but actually it turns out not to be. What we're going to do is we're going to look at 3 fields: promo, state holiday, and school holiday. And so basically what we have is a table of, for each store, for each date, does that store have a promo going on at that date?
Okay.
Is there a school holiday in that region of that store at that date? Is there a state holiday in that region for that store at that date? Okay.
All these are
And
good,
so
right?
this kind of thing is, you know, like they're events. And time series with events.
School holiday means there won't be kids coming back from school to buy stuff, which is bad. But state holiday means people coming to buy stuff, which is good. Let's see.
Events are like very, very common. Like if you're looking at oil and gas drilling data, you're trying to say like the flow through this pipe, you know, here's an event representing when it set off some alarm, you know, or here's an event where the drill got stuck, or whatever, right? And so like most time series at some level will tend to represent some events. So the fact that an event happened at a time is is interesting itself, but very often a time series will also show something happening before and after the event. So for example, in this case, we're doing grocery sales prediction. If there's a holiday coming up, it's quite likely that sales will be higher before and after the holiday and lower during the holiday if this is a city-based store, right? Because you're going to stock up before you go away to bring things with you. Then when you come back, you've got to refill the fridge, for instance, right? So it's, although like we don't necessarily have to do this kind of feature engineering to create
I think I'll mute myself to save you the annoying sound of me eating stuff. So, okay.
Features specifically about like this is before or after a holiday. The neural net, the more we can give the neural net like the kind of information it needs, the less it's going to have to learn it. The less that it's going to have to learn it, the more we can do with the data we already have, the more we can do with the the size architecture we already have. So feature engineering, even with stuff like neural nets, is still important because it means that we'll be able to do get better results with whatever limited data we have, whatever limited computation we have. So the basic idea here, therefore, is when we have events in our time series, is we want to create 2 new columns for each event. How long is it going to be until the next time this event happens? And how long has it been since the last time that event happened? So in other words, how long until the next state holiday? How long since the previous state holiday? Okay, so that's not something which I'm aware of as existing as a library or anything like that. So I wrote it here by hand, right? And so importantly, I need to do this by store, right? So I want to say like, because, for this store, when was this store's last promo? So how long has it been since the last time it had a promo? How long it will be until the next time it has a promo, for instance. All right, so here's what I'm going to do. I'm going to create a little function that's going to take a field name, and I'm going to pass it each of promo and then state holiday and then school holiday. Right, so let's do school holiday, for example. So we'll say field equals school holiday, and then we'll say get elapsed school holiday, comma, after. So let me show you what that's going to do. So we've got to first of all sort by store and date, right? So now when we loop through this, we're going to be looping through within a store. So store number 1, January the 1st, January the 2nd, January the 3rd, and so forth. And as we loop through each store, we're basically going to say like, is this row a school holiday or not? And if it is a school holiday, then we'll keep track of this variable called last date, which says this is the last date where we saw a school holiday. Okay, and so then we're basically going to append to our result the number of days since the last school holiday. That's the kind of basic idea here. So there's a few interesting features. One is the use of zip, right? So I could actually write this much more simply, right? I could say, let's go through, well, we could basically go through like for row in df.iter rows.
Like, I don't even know what zip is supposed to stand. I mean, not what it stands for, what it's supposed to do here.
Right, and then grab the fields we want from each row. It turns out this is 300 times slower than the version that I have. And basically, like, iterating through a data frame and extracting specific fields out of a row has a lot of overhead. What's much faster is to iterate through a NumPy array. So if you take a series like df.store and add .values after it, that grabs the NumPy array of that series. Okay, so here are 3 NumPy arrays. One is the store IDs. One is whatever field is, in this case, let's say school holiday. And one is the date. So now what I want to do is loop through the first one of each of those lists, and then the second one of each of those lists, and then the third one of each of those lists. And like, this is a really, really common pattern. I need to do something like this in basically every notebook I write. And the way to do it is with zip. Right? So zip means loop through each of these lists one at a time. And then this here is where we can grab that element out of the first list, the second list, and the third list. Okay. So if you haven't played around much with zip, that's a really important function to practice with. Like I say, I use it in pretty much every notebook I write all the time. You have to loop through
different lists, right? That's what it's used for?
A bunch of lists at the same time. All right, so we're going to loop through every store, every school holiday, and every...
Because, like, it's possible to do it with one loop. You just say that index of these three lists, but apparently it's slower. Pretty cool.
Date, yes.
So is it looping through like all the possible combinations of each of those, or just
No.
for 1, 1, 1?
Yeah,
2,
exactly.
2,
1,
3,
1,
3?
2, 2, yeah.
Okay.
Yeah, exactly. Thanks for the question. So in this case, we basically want to say, let's grab the first store, the first school holiday, the first date, right? So for store 1, January the 1st, school holiday was true or false, right? And so if it is a school holiday, I'll keep track of that fact by saying the last time I saw a school holiday was that day, okay? And then append how long has it been since the last school holiday, right? And if the store ID is different to the last store ID I saw, then I've now got to a whole new store, in which case I have to basically reset everything. Okay, could you pass that to Karen?
This is for...
What will happen to the first points that we don't have a last holiday?
Yeah, so I just set, I basically set this to some arbitrary starting point. It's going to end up with like the, I can't remember, it's either largest or the smallest possible date.
Okay, thanks.
And you may need to
1970?
replace this with a missing value afterwards, or some, with a 0 or whatever. The nice thing is though.
But is this for... Which holiday are we doing this? Why did I lose it? Or are we just saying... Okay, I'm lost.
Thanks to values, it's very easy for a neural net to kind of cut off extreme values. So in this case, I didn't do anything special with it. I ended up with these like negative a billion day time stamps, and it still worked fine. Okay, so we can go through, and so the next thing to note is there's a whole bunch of stuff that I need to do to both the training set and the test set, right? So in the previous section, I actually kind of added this little loop where I go, for each of the training data frame and the test data frame, do these things, right? So I kind of...
How long it's been since we've had a promo? Yes.
Each cell I did for each of the data frames. I've now got a whole series of cells that I want to run, first of all, for the training set and then for the test set. So in this case, the way I did that was I had two different cells here. One which set df to be the training set, one which set to be the test set. And so the way I use this is I run just this cell, right? And then I run all the cells underneath, right? So it does it all to the training set. And then I come back and run just this cell and then run all the cells underneath, okay?
But my question is... Oh, okay, nothing. I thought we're doing the split here, but it's already been split. Sorry.
So like this notebook is not designed to be just run from top to bottom, but it's designed to be run in this particular way. And I mentioned that because like this can be a handy trick to know. Like you could of course put all the stuff underneath in a function that you pass the data frame to and call it once with a test set and once with a training set. But I kind of like to experiment a bit more interactively, look at each step as I go. So this way is an easy way to kind of run something on two different data frames without turning it into a function. Okay. So this is going to, if I sort by store and by date, then this is keeping track of the last time something happened. And so this is therefore going to end up telling me how many days was it since the last school holiday. Right? So now if I sort date descending and call the exact same function.
Oh, wait, let me go back. Did we?
Sort date since the last.
So this was just a function that we wrote for any of them. Ah, I thought it was static. Okay.
School holiday. Right? So now if I sort date descending and call the exact same function, then it's going to say how long until the next.
Okay, so how long it's been since and how long until before and after.
School holiday.
Okay.
Right? So that's a kind of a nice little trick for adding these kind of event timers, arbitrary event timers into your time series models. Right? So if you're doing, for example, the Ecuadorian groceries competition right now, maybe this kind of approach would be useful for various events in that as well. Do it for state holiday, do it for promo. There we go. Okay. The next thing that we look at here is rolling functions. So rolling functions is how we, rolling in pandas is how we create what we call windowing functions. So Let's
And-
say I
Oh, like oh, I forgot. There's a word for it. Like is it a rolling summation? I feel like I've heard that somewhere.
had some data, you know, something like this, right? And this is like date, and I don't know, this is like sales or whatever. What I could do is I could say like, okay, let's create a window around this point of like 7 days, right? So it'd be like, okay, this is a 7-day window, say, right? And so then I could take the average sales in that 7-day window, right? And then I could like do the same thing, like, I don't know, over here, right? Take the average sales over that 7-day window, right? And so if we do that for every point and join up those averages, you're going to
They look like airplanes. I'm distracted.
end up with a moving average. Okay, so the kind of the more generic version of the moving average.
And like technically everyone would get their 7-day window, so days can overlap. That's why it's called a running window.
Is a window function, i.e. something where you apply some function to some window of data around each point. Now, very often the windows that I've shown here are not actually what you want. If you're trying to build a predictive model, you can't include the future as part of a moving average.
Fair.
Right? So quite often you actually need a window
Upper limit.
that ends here. So that would be our window function.
Oh.
Right? And so Pandas lets you create arbitrary window functions using this rolling here. This here says how many time steps do I want to apply the function to. Right? This here says if I'm at the edge, so in other words, if I'm like out here, should you make that a missing value because I don't have 7 days to average over, or what's the minimum number of time periods to use? So here I said 1. Okay, and then optionally you can also say, do you want to set the window at the start of a period, or the end of a period, or the middle of the period? Okay, so and then within that you can then apply whatever function you like. Okay, so here I've got my weekly by store sums. Okay, so there's a nice easy way of getting kind of moving averages or whatever else. And I should mention in Pandas, if you go to the time series page on Pandas, there's literally like, look at just the index here. Time series functionality is all of this, like there's lots. Because like Wes Bikini, who created this, he was originally in hedge fund trading, I believe. And his work was all about time series. And so I think like Pandas originally was very focused on time series, and still, it's perhaps the strongest part of Pandas. So if you're playing around with time series computations, you definitely owe it to yourself to try to learn this entire API. And like there's a lot of kind of conceptual pieces around like timestamps and date offsets and resampling and stuff like that to kind of get your head around, but it's totally worth it because otherwise you'll be writing this stuff as loops by hand. It's going to take you a lot longer than leveraging what Pandas already does. And of course, Pandas will do it in highly optimized C code for you, vectorized C code, whereas your version is going to loop in Python. So definitely worth, if you're doing stuff in time series, learning the full Pandas time series API. So it's about as strong as any time series API out there. Okay, so at the end of all that, you can see here's those kind of starting point values I mentioned, slightly on the extreme side. And so you can see here the 17th of September, store 1 was 13 days after the last school holiday, the 16th was 12, 11, 10, so forth. Okay, we're currently in a promotion, right? Here, this is 1 day before a promotion. Here we've got 9 days after the last promotion, and so forth. Okay? So that's how we can add kind of event counters to a time series. And probably always a good idea when you're doing work with time series. So now that we've done that, we've got lots of columns in our data set. And so we split them out into categorical versus continuous columns. We'll talk more about that in a moment in the review section. But so these are going to be all the things I'm going to create an embedding for. Okay? And these are all of the things that I'm going to feed directly into the model. So for example, we've got like...
These look very numbery. right? Or binary.
Competition distance, so that's distance to the nearest competitor. Maximum temperature, and here we've got day of week, right? So so here we've got maximum temperature. Maybe it's like 22.1 because I use centigrade in Germany. We've got distance to nearest competitor, might be 321 kilometers, 0.7. Right? And then we've got day of week, which might be, I don't know, maybe Saturday is a 6. Okay. So these numbers here are going to go straight into our vector, right? The vector that we're going to be feeding into our neural net. Right? 22.1, 321.7.
I'm just thinking, like, if this data set was like, for me, if I had to work with a data set, or because okay, my brain, when you ask a function, like a time related function, to tell you the number of the day in the week, I guess you have to say what is the first day or the first day of the week, but I'm guessing by default it assumes Monday is the first day, right? So if it was not Germany, if it was somewhere in Middle East, it would probably matter, but right now it doesn't. Okay.
We'll see in a moment. We'll normalize them, but more or less. But this categorical variable, we're not. We need to put it through an embedding, right? So we'll have some embedding matrix, right, of if there are 7 days by, I don't know, maybe dimension 4 embedding, okay? And so this will look up the 6th row to get back the 4 items, right? And so this is going to turn into length 4 vector, which we'll then add here. Okay, so that's how our continuous and categorical variables are going to work.
Yeah, I need you to repeat that for me again.
Right, so we'll have some embedding matrix, right, of if there are 7 days by, I don't know, maybe dimension 4 embedding, okay? And so this will look up the 6th row to get back the 4 items, right? And so this is going to turn into length 4 vector, which we'll then add here. Okay, so that's how our continuous and categorical variables are going to work. So then all of our categorical variables, we'll turn them into pandas categorical variables in the same way that we've done before. And then we're going to apply the same mappings to the test set, right? So if Saturday is a 6 in the training set, this apply cats makes sure that Saturday is also a 6 in the test set. For the continuous variables, make sure they're all floats because PyTorch expects everything to be a float. So then, this is another little trick that I use. Both of these cells define something called joined SAMP. One of them defines them as the whole training set. One of them defines them as a random subset. Right? And so the idea is that I do all of my work on the sample, make sure it all works well, play around with different hyperparameters and architectures, and then when I'm like, okay, I'm very happy with this, I then go back and run this line of code to say, okay, now make the whole data set be the sample, and then rerun it. Okay, so this is a good way, again, similar to what I showed you before. It lets you use the same cells in your notebook to run, first of all, on a sample, and then go back later and run it on the full data set. Okay, so now that we've got that joined SAMP, we can then pass it to procdf, as we've done before, to grab the dependent variable, to deal with missing values. And in this case, we pass one more thing, which is do scale equals true. Do scale equals true will subtract the mean and divide by the standard deviation. And so the reason for that is that if our first layer, it's just a matrix multiply, right? So here's our set of weights. And our input is like, I don't know, it's got something which is like 0.001, and then it's got something like which is like 10 to the 6, right? And then our weight matrix has been initialized to be like random numbers between 0 and 1, right? So we've got like 0.6, 0.1, etc. Then basically this thing here is going to have gradients that are 9 orders of magnitude bigger than this thing here, which is not going to be good for optimization. Okay, so by normalizing everything to be mean of 0, standard deviation of 1 to start with, then that means that all of the gradients are going to be, you know, on the same kind of scale. We didn't have to do that in random forests, right? Because in random forests, we only cared about the sort order. We didn't care about the values at all. Right? But with linear models and things that are built out of layers of linear models, like i.e. neural nets, we care very much about the scale. Okay, so dscale equals true normalizes our data for us. Now, since it normalizes our data for us, it returns one extra object, which is a mapper, which is an object that contains, for each continuous variable, what was the mean and standard deviation it was normalized with. The reason being that we're going to have to use the same mean and standard deviation on the test set, all right? Because we need our test set and our training set to be scaled in the exact same way, otherwise they're going to have different meanings. Okay, and so these details about making sure that your test and training set have the same categorical codings, the same missing value replacement, and the same scaling normalization are really important to get right, because if you don't get it right, then your test set is, you know, not going to work at all. Okay. But if you follow these steps, you know, it'll work fine. We also take the log of the dependent variable, and that's because in this Kaggle competition, the evaluation metric was root mean squared percent error. So root mean squared percent error means we're being penalized based on the ratio between our answer and the correct answer. We don't have a loss function in PyTorch called root mean squared percent error. We could write one, but easier is just to take the log of the dependent, because the difference between logs is the same as the ratio. Okay, so by taking the log, we kind of get that for free. You'll notice like the vast majority of regression competitions on Kaggle use either root mean squared percent error or root mean squared error of the log as their evaluation metric. And that's because in real world problems, most of the time we care more about ratios than about raw differences. Right? So if you're designing your own project, it's quite likely that you'll want to think about using log of your dependent variable. So then we create a validation set, and as we've learned before, most of the time if you've got a problem involving a time component, your validation set probably wants to be the most recent time period rather than a random subset. Okay, so that's what I do here. When I finished modeling and I found an architecture and a set of hyperparameters and a number of epochs and all that stuff that works really well, if I want to make my model as good as possible, I'll retrain on the whole thing, right, including the validation set. Right? Now currently, at least fast.ai assumes that you do have a validation set, so my kind of hacky workaround is to set my validation set to just be one index, which is the first row, okay, and that way like all the code keeps working, but there's no real validation set. So obviously if you do this, you need to make sure that your final training is like the exact same hyperparameters, the exact same number of epochs, exactly the same as the thing that worked, because you don't actually have a proper validation set now to check against.
Okay. I have a question regarding getElapsed function, which we discussed before. So in getElapsed function, we are trying to find when is the next holiday, like when will the next holiday come?
How many days away is it?
So every year the holidays are more or less fixed. Like there will be a holiday on 4th of July, 25th of December, and there is hardly any change. So can't we just look from previous years and just get a list of all the holidays that are going to occur this year?
Maybe. I mean, in this case, I guess like that's not true of promo, right? And some holidays change, like Easter, you know. So like this way, I get to write one piece of code that works for all of them, you know. And it doesn't take very long to run. So yeah. So there might be ways if your data set was so big that this took too long, you could maybe do it on 1 year and then kind of somehow copy it. But yeah, in this case, there was no need to. And I always value my time over my computer's time. So I try to keep things as simple as I can. Okay.
That's a good note.
So now we can create our model. And so to create our model, we have to create a model data object, as we always do with fast.ai. So a columnar model data object is just a model data object that represents a training set, a validation set, and an optional test set of standard columnar, structured data. Okay, and we just have to tell it which of the variables should we treat as categorical. Okay, and then pass in our data frames. So for each of our categorical variables, here is the number of categories it has. Okay. So for each of our embedding matrices, this tells us the number of rows in that embedding matrix. And so then we define what embedding dimensionality we want. If you're doing like natural language processing, then the number of dimensions you need to capture all the nuance of what a word means and how it's used has been found empirically to be about 600. It turns out that when you do NLP models with embedding matrices that are smaller than 600, you don't get as good a results as you do if they're the size 600. Beyond 600, it doesn't seem to improve much. I would say that human language is one of the most complex things that we model. So I wouldn't expect you to come across many, if any, categorical variables that need embedding matrices with more than 600 dimensions. At the other end, some things may have pretty simple kind of causality, right? So for example, let's have a look. State holiday, maybe if something's a holiday, then it's just a case of like, okay, at stores that are in the city, there's some behavior, there's stores that are in the country, there's some other behavior, and that's about it. Like maybe it's a pretty simple relationship. So like ideally, when you decide what embedding size to use, you would kind of use your knowledge about the domain to decide like how complex is the relationship, and so how big embedding do I need, right? In practice, you almost never know that, right? Like you would only know that because maybe somebody else has previously done that research and figured it out, like in NLP. Right. So in practice, you probably need to use some rule of thumb. Okay, and then having tried your rule of thumb, you could then maybe try a little bit higher and a little bit lower and see what helps. So it's kind of experimental. So here's my rule of thumb. My rule of thumb is look at how many discrete values the category has, i.e. the number of rows in the embedding matrix, and make the dimensionality of the embedding half of that. Right, so for day of week, which is the second one, 8 rows and 4 columns. So here it is there, right? The number of categories divided by 2. But then I say, don't go more than 50, right? So here you can see for store, there's 1,000 stores, I only have a dimensionality of 50. Why 50? I don't know, it seems to have worked okay so far. Like, you may find you need something a little different. Actually, for the Ecuadorian groceries competition, I haven't really tried playing with this, but I think we may need some larger embedding sizes. But it's something to fiddle with. Prince, can you pass that left?
So as your variables, the cardinality size becomes larger and larger, you're creating more and more bigger and bigger wider embedding matrices. Yeah. Aren't you therefore massively risking overfitting because you're just introducing so many parameters that the model can never possibly capture all that variation unless your data is absolutely huge?
That's a great question. And so let me remind you about my kind of like golden rule of the difference between modern machine learning and old machine learning. In old machine learning, we control complexity by reducing the number of parameters. In modern machine learning, we control complexity by regularization. So the short answer is no. I'm not concerned about overfitting because the way I avoid overfitting is not by reducing the number of parameters, but by increasing my dropout or increasing my weight decay. Okay. Now, having said that, like there's no point using more parameters for a particular embedding than I need, like because regularization like is penalizing a model by giving it like more random data or by actually penalizing weights. So we'd rather not use more than we have to. But the kind of my general rule of thumb for designing an architecture is to, be generous on the side of the number of parameters. But yeah, in this case, if after doing some work, we kind of felt like, what? The store doesn't actually say.
Yeah, I was about to say, and if you have time, play with the numbers. Maybe you find a better one.
Seem to be that important, then I might manually go and change this to make it smaller, or if I was really finding there's not enough data here, I'm either overfitting or I'm using more regularization than I'm comfortable with, again, then you might go back. But I would always start with like being generous with parameters. And yeah, in this case, this model turned out pretty good. Okay, so now we've got a list of tuples containing the number of rows and columns of each of our embedding matrices. And so when we call getLearner to create our neural net, that's the first thing we pass in, right? Is how big is each of our embeddings, okay? And then we tell it how many continuous variables we have. We tell it how many activations to create for each layer, and we tell it what dropout to use for each layer, okay? And so then we can go ahead and call fit, okay? So then we fit for a while, and we're kind of getting something around the 0.1 mark. All right. So I tried running this on the test set, and I submitted it to Kaggle during the week, actually last week. And here it is. Okay. Private score 107, public score 103. Okay. So let's have a look and see how that would go. So 107, private 103, public. So let's start on public, which is 103. Not there. Out of 3,000. Got to go back a long way. Here it is, 103. Okay, 340th. Ah, that's not good.
Not the
So on the public leaderboard, 340th. Let's try the private leaderboard, which is 107. Oh, 5th.
Why?
So, like, hopefully you're now thinking, oh, there are some Kaggle competitions finishing soon, which I entered, and I spent a lot of time trying to get good results on the public leaderboard. I wonder if that was a good idea. And the answer is no, it wasn't. Right? The Kaggle public leaderboard is not meant to be a replacement for your carefully developed validation set. Right? So, for example, if you're doing the iceberg competition, right, which ones are ships, which ones are icebergs, then they've actually put something like 4,000 synthetic images into the public leaderboard and none into the private leaderboard. Right? So this is one of the really good kind of things that tests you out on Kaggle is like, are you creating a good validation set and are you trusting it, right? Because if you're trusting your leaderboard feedback more than your validation feedback, then you may find yourself in 350th place when you thought you were in 5th, right? So in this case, we actually had a pretty good validation set, right? Because as you can see, it's saying like somewhere around 0.1, and we actually did get somewhere around 0.1. Okay, and so in this case, the validation set, the public leaderboard in this competition was entirely useless. Yep.
And
Can you use the box, please?
So in regards to that, how much does the top of the public leaderboard actually correspond to the top of the private leaderboard? Because in the churn prediction challenge, there's like 4 people who are just completely above everyone else.
It totally depends. You know, like if they randomly sample the public and private leaderboard, then it should be extreme.
I just noticed that this guy has submitted 196 entries, which is a lot. So maybe they are automating it somehow?
Extremely indicative, right? But it might not be, right? So in this case, okay, well, it's crashed. Oh, here it comes. So in this case, the person who was second on the public leaderboard did end up winning. SDNT
that person as well
came 7th, right? So, in fact, you can see the little green thing here, right? Whereas this guy jumped 96 places. If we had entered with the neural net we just looked at, we would have jumped 350 places. So it just depends. And so often, like, you can figure out whether the public leaderboard, like sometimes they'll tell you the public leaderboard was randomly sampled, sometimes they'll tell you it's not. Generally, you have to figure it out by looking at the correlation between your validation set results and the public leaderboard results to see how well they're correlated. Sometimes if like 2 or 3 people are way ahead of everybody else, they may have found some kind of leakage or something like that. Like that's often a sign that there's some trick.
fair.
Okay, so that's Rossmann, and that brings us to the end of all of our material. So let's come back after the break and do a quick review, and then we will talk about ethics and machine learning. So let's come.
Quick review. Oh, let me see. Okay, I can do that. Because in my head, I have another 20 minutes left in me. And if it ends now, then I'll have to go.
Come back in 5 minutes.
Okay.
So we've learnt 2 ways to train a model.
Have we?
One is by building a tree,
Huh?
and one is with SGD. Okay, and so the SGD approach is a way we can train a model which is a linear model or a stack of linear layers with nonlinearities between them. Whereas tree building specifically will give us a tree. Right? And then tree building we can combine with bagging to create a random forest, or with boosting to create a GBM, or various other slight variations such as extremely randomized trees. So it's worth like reminding ourselves of like what these things do. So like let's look at some data. So if we've got some data like so, actually let's look specifically at categorical data, right? Okay, so categorical.
Oh, sorry, my voice is quiet. I just want to say thanks for sharing a couple of resources down below in your section I've seen before. Hi, Skull Crusher, first time chatter. Sorry for the low voice. My mic is somewhere that, yeah. No, I don't have roommates. I think, I'm sorry. No problem regarding the resources. Whether it's regarding what I'm watching right now, which is fast.ai's intro to machine learning, or the things that I'm using, OBS, ZEPETO, that thing. What? Shoot, I'm really sorry. Wait, what mic am I using? I mean, I feel so bad now. Okay, I'm using Mac. I could change the. Oh yeah, because it's coming from OBS. Oh, I'm really sorry. Please do leave. Go ahead, because you said you were about to leave. Thank you for stopping by. The volume of one, because the volume of the oh, I can make it lower. Okay, let me check. So now this is like, let me
data. So if we've got some data
now?
like so.
Say something.
So if we've got some data.
Oh, I'm really sorry for making it a bad experience. I had a mic. I had a proper mic, but I left it somewhere, and I haven't gotten it back yet. I have a meeting microphone, but last time I used it, it sounded odd. The Mac microphone sounds better, but like you said, I was probably sitting. Yeah. Okay. If you have like 2 minutes, I'm gonna test the other mic if you don't mind. But if you need to leave, it's okay. I can check it myself. Please do whatever is needed for you. And also, I like your name. I'm gonna test the other mic. Volume. Can you hear the rain? Wow, it's loud. Testing. I'm not. Okay. See ya. Thank you. Alright, so I'm gonna be listening to my own voice. Sorry about that. Oh god! Oh wow! Thank you!
Skull Crusher for Life just
that's
followed.
amazing!
CL welcomes you.
Thank you! Thanks again. For the follow. Sound. USB audio device. Testing. USB audio device. Hello. I can't hear myself? Can I hear myself? No? Can't hear myself? Can I hear myself? No? Oh, okay. And I'm gonna test the other mic, and you can hear me hear myself, which is annoying. I'm gonna test the other mic, and you can hear me hear myself, which is annoying. Yep. Testing 1 2 3. Testing 1 2 3. This is a different. They're both low, but you can hear everything with this one. Okay, we're back to the other one. Okay, actually that one's better. I should definitely use this and stop hearing myself. I think what we learned is that I shouldn't have Jeremy be loud. Okay. Thank you, Skull Crusher, for the follow and for telling me about the issue. I thought my issue was that I couldn't see chat, but apparently the issue was that I was so quiet, which is there's a word for it. You know, art mimicking life and life mimicking art. I'm just saying I'm quiet always, so it's okay. Back to the show, which is Jeremy doing a review of everything we've learned so far. And yeah, I did want to check something and hide my screen while I'm checking it. Oh shoot, what did I do? Okay. Hey, I'm back. Yesterday when I was checking what to wear on this character, and I just chose this hoodie like without thinking about it. Then I realized it's the Korea. See? It has Korea's logo on it. I was like, oh, that's so cute. Because each time Korea has a game, I always support them. So I don't know if this is supposed to be the national team, or is this supposed to be like Korea University? I have no idea. Still, it's fun. Okay. I mean, the app is a Korean app, so it makes sense.
Like so. Actually, let's look specifically. Let's look specifically at categorical data, right? Okay. So categorical data. There's a couple of possibilities of what categorical data might look like. It could be like, okay, so let's say we've got zip code. Like, so we've got line 4003 is our zip code, right? And then we've got like sales, right? And it's like 50, and like 94131, sales are 22, and so forth, right? So we've got some categorical variable. So there's a couple of ways we could represent that categorical variable. One would be just to use the number, right? And like maybe it wasn't a number to start, maybe it wasn't a number at all. Maybe our categorical variable is like San Francisco, New York, Mumbai, and Sydney. right? But we can turn it into a number just by like arbitrarily deciding to give them numbers, right? So like it ends up being a number. So we could just use that kind of arbitrary number. So if it turns out that zip codes that are numerically next to each other have somewhat similar behavior, then the zip code versus sales chart might look something like this.
Sales per zip code, okay.
For example, right? Or alternatively, if the zip code versus sales, if the two zip codes next to each other didn't have in any way similar sales behavior, you would expect to see something that looked more like this. Like kind of just all over the place, right?
Huh.
Okay, so they're the kind of two possibilities. So what a random forest would do, if we had just encoded zip in this way, is it's going to say, all right, I need to find my single best split point. Okay, the split point that's going to make the two sides have as small a standard deviation as possible, or mathematically equivalently have the lowest root mean squared error. So in this case, it might pick here as our first split point, because on this side there's one average, and on the other side there's the other average. Okay, and then for its second split point, it's going to say, okay, how do I split this? And it's probably going to say, I would split here, right? Because now we've got this average versus this average, right? And then finally, it's going to say, okay, how do we split here? And it's going to say, okay, I'll split there, right? So now I've got that average and that average. Okay, so you can see that it's able to kind of hone in on the set of splits it needs, even though it kind of does it greedily, top down, one at a time, right? The only reason it wouldn't be able to do this is if like it was just such bad luck that the two halves were kind of always exactly balanced, right? But even if that happens, it's not going to be the end of the world, because it'll split on something else, some other variable, and next time around, you know, it's very unlikely that it's still going to be exactly balanced in both parts of the tree, right? So in practice, this works just fine. In the second case,
trees are really fun to explain as well. Yeah. Okay.
right? It can do exactly the same thing, right? It'll say like, okay, which is my best first split, right? Even though there's no relationship between one zip code and its neighboring zip code numerically, we can still see here if it splits here, right? There's the average on one side, and the average on the other side is probably about here, right? And then where would it split next? Probably here, right? Because here's the average on one side, here's the average on the other side, right? So again, can do the same thing, right? It's going to need more splits because it's going to end up having to kind of narrow down on each individual large zip code and each individual small zip code, but it's still going to be fine, okay? So when we're dealing with building decision trees for random forests or GBMs or whatever, we tend to encode our variables just as ordinals, okay? On the other hand, if we were doing a neural network, or like the simplest version, like a linear regression or a logistic regression, the best it could do is that, right? Which is no good at all. And ditto with this one. It's going to be like that. Okay.
Yeah, especially this part, because this peak is higher than this peak. That would be like a lot of not good.
So an ordinal is not going to be a useful encoding for a linear model or something that stacks linear and nonlinear models together. So instead, what we do is we create a one-hot encoding, right? So we'll say like, you know, here's 1, 0, 0, 0, here's 0, 1, 0, 0, here's 0, 0, 1, 0, 0, 0, 0, 1. Okay, and so with that encoding, it can effectively create like a little histogram, right? Where it's going to have a different...
Is this written backwards? I don't get... This is not binary, is it?
Coefficient for each level. Okay, and so that way it can do exactly what it needs to do. Can you pass that back, please?
At what point does that become like too tedious for your system? Or does it not?
Pretty much never.
Okay.
Yeah.
He did say he respects his time, not the system's time, so the computer should be okay. Unless we find a better way.
Because remember, in real life, we don't actually have to create that matrix. Instead, we can just, you know, have the 4 coefficients, right, and just do an index lookup to grab the second one, which is mathematically equivalent to multiply by the one-hot encoding. Okay, so that's no problem.
Okay.
One thing to mention, I know you guys have kind of been taught quite a bit of more like analytical solutions to things. And in analytical solutions to like a linear regression, you get, you can't solve something with this amount of collinearity. In other words, Sydney, something is Sydney if it's not Mumbai or New York or San Francisco. So in other words, there's 100% collinearity between the fourth of these classes versus the other three. And so if you try to solve a linear regression analytically that way, the whole thing falls apart. Now note, with SGD, we have no such problem. Okay, like SGD, why would it care, right? We're just taking one step along the derivative. It cares a little, right? Because like in the end, the main problem with collinearity is that there's an infinite number of equally good solutions. Right? So in other words, we could increase all of these and decrease this, or decrease all of these and increase this, and they're going to balance out, right? And when there's an infinitely large number of good solutions, it means there's a lot of kind of flat spots in the loss surface, and it can be harder.
Can you hear the motorcycle go by? Because I bet it was louder before, but not right now. I hope my voice is good. Because I think maybe Jeremy's is louder.
To optimize, right? So that's a really easy way to get rid of all of those flat spots, which is to add a little bit of regularization. So if we added a little bit of weight decay, like 1e neg 7 even, then that basically says these are not all equally good anymore. The one which is the best is the one where the parameters are the smallest and the most similar to each other. And so that'll, again, move it back to being a nice loss function. Yes?
Could you just clarify that point you made about why one-hot coding wouldn't be that tedious?
Sure. If we have a one-hot encoded vector, right?
Of what size?
And we are multiplying it by a set of coefficients, right? Then that's exactly the same thing as simply saying, let's grab the thing where the 1 is, right? So in other words, if we had stored this as a 0, and this one as a 1, and this one as a 2, right? Then it's exactly the same as just saying, hey, look up that thing in the array. Okay. And so we call that version an embedding, right? So an embedding is a weight matrix you can multiply by a one-hot encoding, and it's just a computational shortcut, okay? But it's mathematically the same. So there's a key difference. So the first, key difference is between like solving linear type models analytically versus with SGD. With SGD, we don't have to worry about collinearity and stuff, or at least not nearly to the same degree. And then the difference between solving a linear or single layer or multi-layer model with SGD versus a tree is going to be like, it's going to complain about less things, right? So in particular, you can just use ordinals as your categorical variables. And as we learned just before, we also don't have to worry about normalizing continuous variables for a tree, but we do have to worry about it for these SGD trained models.
I guess there's a lot more pre-processing when it comes to not trees. But trees don't complain. And we still cut them down. Okay.
So then we also learned a lot about interpreting random forests in particular. And if you're interested, you may be interested in trying to use those same techniques to interpret neural nets, right? So if you want to know which of my features are important in a neural net, you could try the same thing. Try shuffling each column in turn and see how much it changes your accuracy, okay? And that's going to be your feature importance for your neural net. And then if you really want to have fun, recognize then that shuffling that column is just a way of calculating how sensitive the output is to that input, which in other words is the derivative of the output with respect to that input. And so therefore maybe you could just ask PyTorch to give you the derivatives with respect to the input directly and see if that gives you the same kind of answers, right? You could do the same kind of thing for a partial dependence plot. You could try doing the exact same thing with your neural net, replace everything in a column with the same value, do it for 1960, 1961, 1962, plot that, right? I don't know of anybody who's done these things before, not because it's rocket science, but just because, I don't know, maybe no one thought of it, or it's not in a library, I don't know. But if somebody tried it, I think you should find it useful. It would make a great blog post, maybe even a paper if you wanted to take it a bit further. So there's a thought it's something to do. So most of those interpretation techniques are not particularly specific to random forests. Things like the tree interpreter certainly are, because they're all about like what's inside the tree. Can you pass it to Karen?
As a teacher, he's like amazing about opening doors for his students and giving them ideas that he may not have the time to work on. Like this is from 2018, but like it compels me to look at his newer lectures, because I'm like, what are his suggestions now? What is stuff that others haven't done? Because maybe they're too lazy. I don't know. I don't know. Maybe a lot of things have already been done by now. I don't know.
We're applying tree interpreter for neural nets. How are we going to make inference out of activations that the path follows, for example?
So
how are we going to, like, in tree interpreter, we are like
we're looking at the path.
We are looking at the paths and their contributions
Yeah.
of the features.
Yeah.
In this case, it will be same with activations, I guess, the contributions of each activation and their path.
Yeah, maybe.
How
I don't know. I haven't thought about it.
How can we like make inference out of the activations?
So I'd be careful saying the word inference, because people normally use the word inference specifically to mean the same as like a test time
Okay.
prediction.
Make
You
sense
make some kind of interrogate the model.
Yes.
Yeah. Yeah, no, sure. We should think about that.
Okay.
Actually, Hinton and one of his students just published a paper on how to approximate a neural net with a tree for this exact reason, which I haven't read the paper yet. Could you pass that?
So like get the same answer as a tree, as a neural net from a tree and think that's the explanation? Would that be equivalent?
So in linear regression and traditional statistics, like one of the things that we focused on was statistical significance of like the changes and things like that. And so when thinking about a tree interpreter or even like the waterfall chart, which I guess is just a visualization, I guess where does that fit in? Like, because we can see like, oh yeah, this looks important in the sense that it causes large changes, but how do we know that it's like traditionally statistically significant or anything of that sort?
So most of the time I don't care about the traditional statistical significance, and the reason why is that nowadays the main driver of statistical significance is data volume, not kind of practical importance. And nowadays most of the models you build will have so much data that like every tiny thing will be statistically significant, but most of them won't be practically significant. So my main focus therefore is practical significance, which is, does the size of this influence impact your business? Statistical significance only, like it was much more important when we had a lot less data to work with. If you do need to know statistical significance because, for example, you have a very small data set because it's like really expensive to label or hard to collect or whatever, or it's a medical data set for a rare disease, you can always get statistical significance by bootstrapping, which is to say that you can randomly resample your data set a number of times, train your model a number of times, and you can then see the actual variation in predictions. Okay, so that's with bootstrapping, you can turn any model into something that gives you confidence intervals. There's a paper by Michael Jordan, which has a technique called the bag of little bootstraps, which actually kind of takes this a little bit further. Well worth reading if you're interested. Can you pass it to Prince?
So you said we don't need one-hot encoding metrics if we are doing random forest or if we are doing any tree-based models. What will happen if we do that, and how bad can our model be?
If you do one-hot encoding?
For random forest.
Yeah, we actually did do it. Remember we had that like maximum category size, and we did create one-hot encodings. And the reason why we did it was that then our feature importance would tell us the importance of the individual levels, and our partial dependence plot, we could include the individual levels. So it doesn't necessarily make the model worse. It may make it better, but it probably won't change it much at all. In this case, it hardly.
I think the point is like you don't need to, so why waste the effort?
Changed it.
This is something that we have noticed on real data also, that if cardinality is higher, let's say 50 levels, and if you do one-hot encoding, the random forest performs very badly. And
yeah, that's right. If the cardinal, that's why we have that that's why in fast.ai we have that like maximum categorical size, because at some point your one-hot encoded variables become too sparse, right? So I generally like cut it off at 6 or 7. Also, because like when you get past that, it kind of becomes less useful because the feature importance is going to be too many levels to really look at.
So can it not just not look at those levels which are not important and just give those significant features as important?
Yeah. I mean, it'll be okay. It's just like once the cardinality increases too high, you're just splitting your data up too much, basically. And so in practice, your ordinal version is likely to be better.
Thanks.
Okay, so
Okay.
yeah, so there's no time to kind of review everything, but I think that's the kind of key concepts. And then, of course, remembering that the embedding matrix that we could use is likely to have more than just one coefficient. We'll actually have a dimensionality of a few coefficients, which isn't going to be useful for most linear models. But once you've got multi-layer models, that's now creating a representation of your category, which is kind of quite a lot richer, and you can do a lot more with it.
Cool.
Let's now talk about the most important bit.
No, I refuse, because yeah, I think I can finish. But yeah, the most important bit is
We started off early
there,
in
ethics and data science, which is the second part of this core lesson. But because my plan was to do half of it today and half of it, if nothing goes wrong tomorrow, then that's what I'm gonna do. Because I've been live for an hour, which is pretty good. I came a bit late. I can start earlier tomorrow, inshallah. And sorry for the voice issues. I hi. Almost, yes. Hi, Agrideep is here. How are you? It's been a while, for me even, like because it's been a while since I've been streaming. The stream is ending, but if all goes well, I will continue tomorrow. And if the time is not good for you, you can let me know. I will try to accommodate. I really like when the glass thing is like moving around. Like if I do this, it stays. So the physics is bad, but if I do this, it moves around. Anyway, yes, even though I'm gonna end it in a bit, I still, inshallah, will be back tomorrow to do the second part of this course. And actually, if I go back to the screen, you can help me figure out what to do next, because I have two plans. One of them is taking courses from, oh, let me go back. Hugging Faces, like library, I guess, of courses. And then the other one is this course I found on YouTube, which is from Carnegie Mellon University, by Graham Newberg, I guess, which is in advanced NLP. Oh, I don't know if I should do advanced. Oh, good. Good. My usual time is good. That's good. I actually started a bit late today, because I didn't wake up late, but I forgot that I was planning to stream. And okay, I don't know what time it is in like for you right now, because it's currently 8 a.m. for me.
So the class today is
What did I do? Oh
introduction to
God,
natural
that
language processing,
scared me. I was
and
like,
I'll be
wait, can
talking a
people
little bit
talk to
about,
me?
what.
It was this video. That really scared me. Yes, what I was about to say is, yeah, thank you. Uh, oh. I do that sometimes, don't I? I forget that I should. We're back. There we go. Thank you for stopping by. So I have almost one stream left from Fast AI. You guys are 2.5 hours ahead of me. That's fun. Yeah. So I'll finish that inshallah tomorrow. That's the plan. I want to finish it so that I can go to the next thing, which would either be the NLP course from Hugging Face, or that, because I know Hugging Face would probably be more practical, but if I go back to the screen again, because I just scared myself, what I, no thanks, okay, if I go to this website they have, Let's figure out together, because last time I didn't figure out if I can see the assignments, because I like maybe we have course details. Where's location? Okay. How can we get assignments page? Dude. Oh, wait, is that what just happened here? Okay. So I guess these assignments have links that I can go to, because I see two. Are there 2 assignments? 4 assignments. But at least I see link 1, which is assignment 1. I see assignment 3. I can't see assignment 4 because maybe it hasn't started. Okay, that does seem like there's a practicality. There is a practicality side to this as well. Maybe I can do them in parallel. I don't know. It's raining. Anyway, I'll think about it. Maybe I'll start with Hugging Face and see like what I feel like that day, you know? Because I don't think it's good for me to put myself in box and then feel like I can't breathe. So let's see. Thank you so much for stopping by. I always feel like I don't deserve it. So, can I do this? It's supposed to be a half a heart, isn't it? Yay. But point is, where's the one where I'm supposed to say hello or goodbye? Where is it? Did I lose it? Oh, there it is. Okay. So this is my my thank you and goodbye and hello hand. Thank you for stopping by. And sorry for the voice issue. There were some sound issues. My normal mic is not with me, so I'm using a headset, which the sound feels muffled. And I'll try to fix it, but no promises. Inshallah, we'll continue learning together. And it's raining! Oh my god! Sorry, I don't know if you can hear it. Okay. Have a nice rest of your day. And I'm gonna end the stream. If you have anything, please let me know. Otherwise, I'm gonna end the stream in 5, 4, 3, 2, 1. Goodbye. Thank you.